And in this slide, we will study solenoids, which is a very important device in using magnetic fields. Okay, have you ever heard of solenoids? It is in fact nothing but a coil that is wound to a cylindrical shape, which looks like this. Okay, here the important thing you have to remember is that however long this coil may be, the amount of current is same everywhere. Why? Because when we make such a coil or solenoid, we will use just a single wire and then just simply make turns many times. And when you actually make such turns along each current or each current carrying wire, there will be an encircling magnetic field, right? That's what we learned. So for example, in this figure shown here, on the upper part, magnetic field is going in to the screen, and on the lower part, magnetic field is coming out of the screen. So on the upper part, magnetic field will go around like this, encircling this wire, and then on the lower parts, magnetic field will go around like this. So that is true for any part of the solenoid. So as a result, between this upper and lower part, magnetic field will always effectively going from right to left, right? And then between these wires and outside the solenoid, the pattern is very complicated, right? So we don't want to study such complicated situation. So we will just make things very simple and assume that we have something called the ideal solenoid. Okay, so this will make things very simple. So in order to make it simple, we assume two things. So when we say ideal solenoid, we first assume that this solenoid is infinitely long, and then the wires are very tightly wound. So it is so tightly wound that there is no magnetic field between wires. So it's just like having a long tube like this. Okay, and then by assuming that it's infinitely long, the magnetic field will be same wherever inside this solenoid, whether you are close to the left edge or close to the middle or close to the right edge, magnetic field will always be the same, and it's going, of course, from right to left. Okay, and then another thing is that actually magnetic field has to come around so that the magnetic field, there will be some magnetic field outside, right? But then for ideal solenoid, we will just assume that magnetic field outside is zero. Okay, is it possible? Of course it cannot be zero because the magnetic field has to come around. But of course, if you make the solenoid good enough, the actual size of the magnetic field outside will be very small compared to inside. So effectively, we can say is close to zero. Okay, that's the situation we are assuming, and then we will try to understand how much magnetic field will be there when you have a solenoid for a section of length h, and in this solenoid there are small n turns per unit length. Okay, so in this situation we will use the Ampere's law, and this is the Amperian loop. We have this rectangular red part. Okay, so if we want to integrate magnetic field going around this Amperian loop, we have to do the integration over 4 sections, starting from A, go to B first, and then go to C, go to D, and come back, right? So here I have written that we are dividing this Amperian loop into 4 sections. And in the first part, between A and B, we already said that magnetic field is 0. So this goes to 0, so therefore integration is 0, right? And then how about the second part, going from B to C? Now here, the ds vector is perpendicular to the magnetic field, right? So therefore, their dot product must become 0. Okay. And then let's jump to the fourth section and discuss this again, because it's again on the fourth section, ds vector is perpendicular to the magnetic field. Again, this part, it becomes 0, right? So we have only one part remaining, which is going inside the solenoid from C to D. And then we said that magnetic field is same whether you are close to the left edge or close to the right edge, right? So magnetic field must be constant here. So now it becomes very simple, and at the same time the ds vector here is parallel to the magnetic field, so therefore it is simply constant b multiplied by the length of this section, and then we actually already call it h, right? So finally we get p multiplied by h from this integration, and according to the Ampere's law, this is equal to the magnetic permeability constant multiplied by the enclosed current. So how much current is enclosed inside this Amperian loop? Of course, is according to the figure, it's this much. And then, in fact, this looks like a tube, but in fact, in reality, this is not a tube. This is many tons of wires, and each wire carry the current I, right? So therefore, the total amount of current here is the current multiplied by the number of turns, right? Then how many turns are there? We already said there are n turns per unit length, and then the length of the section is h. So therefore, total number of turns is n multiplied by the h. So therefore, now we have completed the calculation, and finally, if you summarize it, now the magnetic field inside an ideal solenoid. Ideal solenoid is obtained as the permeability constant multiplied by the current and multiplied by the number of turns per unit length. Okay. Okay, we just studied the solenoid, and the solenoid is useful when you try to use the magnetic field inside the coil. Okay, but if you have a coil that actually it does have a magnetic field outside, so and its magnetic field outside will just work like a simple magnet. So in that case, we call it electromagnet, and here we will perform a simulated experiment about the magnetic field of an electromagnet, and then we will compare it with the case of the permanent magnet. But before going there, please make sure you understand that if you call the coil an electromagnet, then we will be talking about its magnetic field outside the coil. But if you call a coil a solenoid, then we will be talking about a magnetic field inside the coil. Okay. So this simulation package is in fact the same thing that we used in the previous slide when we are trying to see the magnetic field around this bar magnet. Okay, do you remember this? So this was a compass, and then by moving the compass around the bar magnet, we got an idea how the magnetic field was oriented around it, right? And we also saw the magnetic field explicitly using this figure, right? Okay, so we will try something similar, and then now this time we will use a coil which we call electromagnet, and this coil is attached to a battery, and then this looks like a solenoid, but in fact this is not an ideal solenoid. Let's call it a real solenoid, because we are trying to see the magnetic field outside this coil, right? Well, first, this ideal solenoid is actually useful when you try to get the magnetic field inside the coil, but that's not what we are doing here. We will try to see the magnetic field outside this coil, so this is not an ideal solenoid. Okay, anyway, so we have this compass again. Now the compass is not responding to anything, right? And that is because the current is not flowing. And these small dots here represent electrons. So remember that direction of electron flow is opposite to the direction of the current. So let's turn this on. So as you can see, these particles flow into the positive terminal of the battery. So therefore, this is the this is the electrons. Okay, these are electrons, and then the direction of this electron flow is opposite to the direction of the current. Okay, And then as you can see now, the direction of this compass has changed. And then if you move this compass around this coil, then you can see how the magnetic field is going. Okay, so here you get the idea. Magnetic field follows the red part of this compass, so it goes around like this. And then on the other side, how about it? On the other side, it's the same thing. Magnetic field goes around like this and comes back here. So which means that this part works like a north pole of the bar magnet, and then this part works like a south pole of the bar magnet, right? Okay. And then in fact, but actually the very nice thing about this electromagnet is that you can actually change the polarity simply by changing the direction of the current. So let's try to change this voltage or potential of this battery from 10 volts to minus 10 volts and see what's going to happen for this compass. Okay, so direction flipped, right? Which means that you can simply change the polarity of this electromagnet by changing the polarity of the battery or the direction of the current. And then if you keep changing between positive and negative current, and you can actually do this by using an alternating current source, which is given here. So yeah, you see, so the current or voltage changes as a function of time continuously, and then the polarity keeps changing between north pole and south pole, right? So this type of alternating current power supply and its combination to the coil will be very useful in the next chapter. So try to remember this. Okay, and then you can also see the magnetic field, yeah, flipping back and forth using this figure. Okay. Okay, we just saw that a current carrying coil can work just like a magnet, and so that's why we called it electromagnet. And what it means is that if you have a current carrying coil, it will have a magnetic dipole moment, just like having north pole and south pole, right? So here, now let's try to calculate the magnetic field when you are sufficiently far away from this magnetic dipole. Okay, so in order to do that, let's bring up our memory and then try to remember what was the magnetic dipole moment, right? So in the previous chapter, the magnetic dipole moment was defined as a current multiplied by the area of this loop, current loop, right? And if there is more than one turns, you have to multiply by the number of turns, which is capital N here. Okay, so it's just like the figure is shown here. Okay, so in this figure we have a current loop. We are looking at it from the side, so current is coming out here and is coming in here, so it's a loop, right? And then if you have a circular loop, area will of course be pi r square. So r is the radius of this loop, right? And then now in this case, what we want to do is that we want to know the magnetic field along the direction of perpendicular to this loop, which is the direction of the magnetic dipole moment, right? And actually the magnetic field along this axis is given like this. I didn't explain yet why we get this, how we got this result, and I will have time to explain this in the classroom. There we will use the Biot-Savart law. So it's a little bit difficult integration, but not too difficult. But I will again explain in the classroom. But right now, let's just take this. Okay, and this equation of the magnetic field is valid whether you are close to the loop or very far away from the loop. But here, what we want to know is what the magnetic field will be when you are very far away from this loop, or equivalently, if you think this magnetic dipole is very small, right? So we will take the mathematical approximation such that the G will be very large compared to the radius of this magnetic dipole. We did something similar when we considered the electric field coming from the electric dipole, right? Do you remember? Okay, anyway, starting from this equation, if you assume Z is much larger than R, then of course this will disappear, right? So then you can finally see that now G to the powers of 3, or G cubed, remains, and then again the area of this loop was pi r square, so you can replace this r square with pi a, right? Okay, and then now assume now you actually have a coil, so therefore you will have n number of turns. Then of course you have to multiply this result by the number of turn n, right? Okay, and once you have written it this way, what is this? This is in fact this magnetic dipole moment, right? So you can replace this by using the magnetic dipole moment, and this magnetic dipole moment is of course a vector. What is the direction of the vector? So if you use a right hand rule, this will be the direction of this magnetic dipole moment vector mu. Okay, so therefore you can finally write that magnetic field along the direction of the magnetic dipole moment, of course, has to be proportional to the magnetic dipole moment itself, and is inversely proportional to the cube of the distance from the magnetic dipole moment. And this dependence of the distance from the dipole moment is again the same as what we have seen in the case of an electric dipole. Okay, let's finally summarize this long lecture. This time the lecture was a little bit long, right? Anyway, let's make a summary. So from this lecture, you have learned the direction of magnetic field around a current, and we also learned how to calculate the magnetic fields using the Biot-Savart law and also using the Ampere's law, right? So try to make sure you understand these two laws. And we also learned the magnetic fields inside ideal solenoid. So we always use this solenoid only to know the magnetic field inside. The magnetic field outside the solenoid is not very useful, so it's always inside. And finally, we learned the magnetic field due to a magnetic dipole moment. Okay, so up to here will be the materials to be covered for the midterm exam. So when I'm recording this lecture, the date for the midterm exam is not exactly decided, but by the time you get to watch this lecture, probably it would have been decided. So please ask the teaching assistant, or please see the announcement in the blackboard, so make sure you understand when the midterm exam will be. Okay, and once you are done with your midterm exam, in the next lecture, we will study these things. So good luck with your midterm exam, and I will see you later.